Hello again and welcome. I purchased this Bryman BM869s on the right roughly 10 years ago today. So back then I was looking for a multimeter with some specific features. This one seemed to be the best out of the ones that I looked at. But another meter that I looked at back then was this Hioki. This is the DT4282. I was seriously considering this meter, mainly because I have experience using the Hioki brand. One of the meters that I have, I had actually ran surge tests on it, so I have a lot of confidence in the brand as far as being a robust meter. And at the time, Briman was kind of an unknown. I really wasn't sure how these meters would hold up, so I ended up buying this BM869s over the Hioki DT4282, mainly because it had a couple of features that I wanted that this Hioki didn't have. So what I'd like to do today is compare these meters and just see, did I really make a good choice in buying this Briman over this Hioki. I guess a couple of things about these meters is, of course, we have two of them. This is the original one that I had purchased, and we can tell that by the decals on the back. Of course, these have worn off. And this is one that Briman had sent me, and we use this to perform that 50,000 life cycle test on the function switch. So this meter has not only been through that, it's also been through transient testing. This particular meter had been damaged at 10,000 volts peak with a 50 microsecond full width half height. I also changed the clamp transistors in this meter, and I ran it up to 14,000 volts and it passed. I've also modified this to have the later firmware, so this has a longer backlight than the original firmware that was supplied with the meters. I also changed the MOVs on this after I smoked them, so the MOVs that are in this meter came out of one of the prototype 780 meters that Briman had supplied me with. So this meter has a few modifications, where this one was damaged at 10,000 volts peak with a 50 microsecond full width half height. I had repaired the meter using the OEM parts, so this meter is basically stock, where this one is not. While this meter is 10 years old, I'd have to go back and look, but this meter is probably in the order of maybe 7 years old. Both of these meters are 100% functional. Well, I've never had these calibrated. I have shown these against my fluke voltage standard over the years and making some other measurements, and I'm sure that both these meters would still meet calibration. So I've had this meter for quite a while. You can see it's still sealed in the original packing. I've always meant to get around to this, but I've just now got some free time, so I thought we'd have a look at it. So these meters are kind of comparable in that both of them can measure decibels. Both have AC plus DC. Both of them can measure conductance. They both can log, assuming that you buy the accessories for them. They both support 4 to 20 milliamp, and they're both a dual display meter. The current price on this Hioki is between $570 and about $650 US. The BM869s on TME is currently selling for about $350. I think I paid about $230 for this when I bought it originally 10 years ago. The Hioki is a 60,000 count meter, where this Bryman BM869s is a 50,000 count meter, but it has this high resolution mode at 500,000 counts. Now that mode cannot be used for every function, but it does work for the DC volts and the DC microvolts, so ranges that I'm actually interested in. Now I've heard people say that this is a gimmick feature. I've actually used this to troubleshoot some drift problems I was seeing. People too were talking about the drift of this. I've shown data off of that where this function is actually quite stable. One of the features that the BM869s has is this bar graph at the bottom, where the Hioki does not have that feature. This bar graph has 41 segments and it's updated at 60 Hertz. So if you're looking at rapid moving changes and the display is not fast enough, that's where I wanted this feature. Again, I had mentioned that both meters measure conductance. If we look at the normal resistance mode, this meter can only read up to 50 meg, where this Hioki can read up to 600 meg. If we look at capacitance, the Briman can read up to 25 millifarad, where the Hioki can read up to 100 millifarad. Now normally I'm not testing capacitors much over 2,000 microfarads, so both of these would be overkill for that. And the same thing for resistors. I do a lot of work with high voltage. I do use some quite high value resistors, and this meter's been fine working with those resistors as far as reading the conductance. The Hioki uses 4 AA batteries, where this Briman uses a single 9 volt. According to Hioki's documentation, This meter has a 100-hour operating. That's without the backlight. I've measured it before with this BM869s, and it looks like about 80 hours, so a little bit shorter run span with that 9-volt battery. So one of the things I was interested in is the lowest operating voltage range. Now, while this Briman has a 500 millivolt range, this Hioki has a 60 millivolt range. But keep in mind, in that 500 millivolt range, this meter also allows this 500,000 count mode, so we can get all the way down to a 1 microvolt resolution with this meter. In the 60 millivolt range, the input impedance of this meter is typically about a giga-ohm, and it's in parallel with 100 picofarads, where the Bryman's 500 millivolt range has a 10 mega ohm input impedance in parallel with 60 picofarads. If you look at the documentation for these two meters, of course that's all available online. The Hioki documentation, I would say, is quite a bit better than what Briman offers. This is very detailed. So let's have a look at what's all supplied with this meter. You can see size-wise, the Hioki is a little shorter, not by much. They are about the same width, roughly the same thickness. On the back here we can see the fuses that are required for the meter. The 11 amp fuse has a breaking current of 30 kA DC, and that's at 1000 volts. The 630 milliamp fuse, again, it's 1000 volts as well at 30 kA. Of course, we get the user's manual. One thing about this manual, this is the English version, so this is not like 10 different languages. Operating precautions, a lot of warnings about using the meter. Of course, if you're using these in a high-risk environment, that may concern you. That's not anything that we're interested in here at the lab. Looks like it also comes with a set of batteries. These are by Toshiba. And then of course we have the two leads with our protective caps. The first thing we're going to do is just see if the meter will power up okay. I assume we just remove these two screws here to get to the battery compartment. Oh yeah, it pops off quite easily. Looks like they're using Holley brand fuses. I've seen these used in other meters as well. We'll just be using a set of rechargeables to test this thing out. And does it turn on? No problems whatsoever. Alright, so what I'd like to do now is just go through a basic functional test with the meter. And for that, we'll just be using our test box. One thing about this right off the bat, you can see it uses the shutters. So if we go to current, again, kind of a idiot-proof system. Let's just start with capacitance. Let's try rel. Alright, let's start. This is going to be 150 picofarads. You can see it measures 146. This will be a 1 nanofarad, and it's reading 0.993. This is a 0.1 microfarad, and you can see it's reading 101.7. Let's try it with some larger parts. This is going to be a 1 microfarad. Spot on. And this will be a 10 microfarad. And that's spot on, and this is a 100 microfarad part. And you can see it's reading 105.4. I've got a larger part here. This is a 2200 microfarad. I just want to see how fast this meter is. There it is. So 2.06. Should be 2.2. Let's just try the same thing with the BM869s. And here we go. Very close reading wise, but you can see the Briman takes 3 readings before it locks in. After that it's pretty stable. Let's just try it again. I'll short the capacitor out. Quite a ways off, a little closer, and 2.075. And again, after that it's pretty stable. Let's just try it with the newer firmware and see if that makes any difference at all. Again, the changes to the input protection on this meter should not affect this capacitance reading whatsoever. Again, we'll just short this out. And here we go. Does it behave the same? I suspect it probably does. Yep. And the third one, it catches it, so yep. So very close between the 2 meters. This one reads a little higher, but they basically behave the same. Let's just try it in resistance. So here's a dead short, and here's an open. Again, a short and an open. See, it auto ranges fairly quickly. Let's just try the same thing with the Briman. And here we are with a short. And here we are with an open. And again a short. And an open. Looks like the Briman is a little bit faster. Again, here we are with the Hioki. Here's with the short. And here's with the open. Probably a wash. Okay, let's just try reading some different values with this. Again, we'll short these out. And we'll select the rel mode. Try to get this up here a little bit closer for you. Okay, so the first one we're going to measure is a 0.01 ohm. And let's try it with a 0.5 ohm. That's a lot better. And try it with a 1 ohm. Again, this is a 1% part. This is a 50 ohm, 0.01%. This is a 100 ohm, 0.01%. Very good. Here's a 1K, 0.1%. Looks good. This is a 10K, 1%. Here we have a 100K, 0.1%. A 1 meg, 1%. Settles out pretty quick. Oh, and a 10 meg, 0.1%. Again, pretty quick. Let's try it with a 100 mega ohm, 5%. Looks good. Let's try a conductance. So, looks like we have to go to capacitance and hit the shift key. Yep, this is a 40 mega ohm. It should give us 25 nanosiemens. Yep, looks good. It's a 100 mega ohm, which will give us 10 nanosiemen. Looks good. And this is our 1 giga ohm. Should give us 1 nanosiemen. Looks good. That's actually very fast. So let's try the same thing with the Briman. See, it drifts a little bit. Again, here's with an open. And again, here's with the 1 giga ohm. There it's settled. And again, back to the Hioki. Here's with the open. And here's our 1 gigaohm. Looks like a little bit of overshoot with this meter. And here we are again. Yep, you can see it kind of overshoots. And then it settles out. Alright, let's try temperature. This should read roughly 500 degrees Celsius. That looks good. And again, this should be roughly 24 degrees C. That looks good. And this will be 1040 degrees C. Oh, looks like it can't read up that high, so 800 degrees Celsius is the maximum. Of course, if we look at that with the BM869s, and you can see roughly 1040 degrees C, so this meter does not have a problem with it. Now, one of the key reasons that I bought this meter, you'll notice it has T1 and T2. So this meter actually has 2 thermocouple inputs. The second channel is on the 2 current jack, so you put a K-type thermocouple across the 2 current inputs, and that gets us T2. The other thing with this meter is it can look at the difference between these 2 probes. I've used that quite a bit since I've gotten this meter. I'm glad I got that feature. This is one of the features that this Hioki does not support. Alright, let's just try measuring the DC voltage. Again, we got to attach to our K-type input. It should be roughly 20 millivolts. That looks fine. Let's just try it with our 5 volt standard here. And that looks, geez. And that looks fine. Let's just try it with our AC input. So this is again switching between ground and 5 volts. So this should give us 2.5 volts. And that is correct. Let's just try it with our high voltage, high frequency. This should give us about 60 volts DC. Close enough. Let's just try it in AC plus DC. So this should give us roughly 90 volts. And you can see it's reading about 85.7 and at about 3.2 kilohertz. That is correct. Let's just try it with the lower frequency. So again, this is going to be DC coupled. Let's see what we get. Should be 2.5 volts and 2.5 volts. Let's just try it with the frequency and the AC plus DC. So this should be roughly 60 hertz. You can see it's 59.99 essentially, and 3.52 volts. That is correct. This is going to be at 30 hertz. That is correct. This will be 15 hertz. That is correct. This will be 120 hertz. And that is correct as well. And you can see the AC plus DC works just fine. Again, AC plus DC, you're taking the square of the DC plus the square of the AC value and taking the square root of that. You can do that with any meter, but normally you don't want to have to carry a calculator around with you. You have a computer sitting right here in your multimeter that can do that calculation. That's definitely a feature that I want in any handheld meter. Let's try diode check, and this is with a short. You can see it glows this nice red. And here's with an open, so very fast. Looks like you can program the threshold. Let's just try it with 1 silicon diode, so this should read 0.7. And you can see it does. This will be 2 silicon diodes in series, and that's fine. And this is going to be our white LED. You can see it lights that up just fine. And you can see it reads roughly 2.6 volts or so. Let's just try current real fast. This should be 100 microamps. And you can see that's spot on. This will be 10 microamps. That looks spot on. Here's 1 microamps. That looks good. And 100 nanoamps. That looks good. I guess we can try the high current mode real quick. Crank this thing all the way up. Again, this will be 100 microamps. Does it flip a count? And it looks like it does flip a count, so at least the fuse in this meter is okay. Here I have my Fluke 731 reference standard. This is currently set for 1 volt, and it's attached to our HP34401A. You can see it's reading 0.999820, and that's with all 3 meters attached in parallel. So So here's our Hioki DT4282 at 0.9997. And here's our Bryman BM869s at 0.99986. So that Briman is actually quite close to our old HP meter. Let's just change this down to 1 millivolt. And you can see it's displaying 1.003337. So here's our Hioki at 1.000 millivolts. And here's our Briman at 0.999. You can see it moves around a significant bit. Let's change this to 10 volts. And you can see we're displaying 10.00015. And again, here's our Hioki at 9.999. And here's our Briman at 10.0014. Again, we are talking about a meter. I've never had these aligned, even after I damaged them. So these still have the original factory cal in them. And we're talking about something that's about 10 years old now. Next, I'd like to just compare the internals of these two meters. Again, here's our little 9-volt transistor battery. And I'm showing you the stock meter. Looks like with this we have 6 screws. It's 2 sunk way down in there. Again, I do like the Hioki brand in general. They do make some very nice products. I want to mention too that I did purchase this meter out of my own pocket. I don't remember where I bought this one from. And I also bought the Briman on the right here, again out of pocket. So I didn't start working with Briman really until after I tested this first meter. And they were interested in the tests that I ran and how their meters compared with other products. That's the only company that has ever expressed any interest in these tests. But since then, they have provided me with a fair number of meters, including this one. This is the new Brymen BM869s BT. Again, this meter is now released in production. You can actually go out and buy this meter. This meter is very similar to this BM789, except that it comes with a Bluetooth module. I've made a few videos demonstrating some of the features of this meter. I'm currently working on writing a document that explains the programming protocol for that meter. So this is the 630 milliamp fuse. Again, this is made by Holly. You can see 1000 volts AC and DC, and the break current is 30,000 amps. Alright, it should just come apart. See how the battery pack attaches. Of course, this is for our optical serial interface. Case is well made. Let's see, now we've got an internal cover. Looks like maybe just one more screw holds this in. This is a busy circuit board. Alright, so let's just look at the input here. So this is our common input here, and this is our high voltage input here. So you can see they're using a single PTC. Here's their surge rated resistor probably, and it looks like a single gas discharge tube right here. And I'm not sure how I really feel about that. Now let's compare that with the Briman. Again, this is our high voltage input. 2 sets of 2 surge rated resistors in series. There's 2 different PTCs and then 3 MOVs. So again, this is basically 2 identical input circuits. You can see one of the PTCs is physically larger than the other one. And then these 2 MOVs here tied to a common point up to this 3rd MOV that goes back to this common point here. Now I know that this meter here is quite robust because we've tested 2 of them now and they've held up very well. I can't say that for this Hioki. We did look at a different Hioki and it held up quite well. I don't remember how that input circuitry compares, but this is definitely a lot less complex, assuming this will hold up. Now again, One of the things to mention with this is these transient generators, these are very low energy, so I'm testing somewhere below about 20 joules with this generator. So again, I want to be clear, this has nothing to do with the IEC standards and the actual surge tests that are performed with these meters for safety testing. This testing has nothing to do with safety. What I'm basically looking at here is how electrically robust these meters are. Again, both these meters now are quite old. There's probably several high-resolution photographs of what the internals look like. I'm not going to attempt to dissect this at all. I wanted to compare the DT4282 against the original Hioki meter I looked at, and this is the DT4252. So this is a lower end meter. Here's the two PTCs. You'll notice that the package size is basically the same. And it looks like they use the same gas discharge tube. But notice the surge rated resistor. So here we have a single part, and here we have these two in series. So I don't know what possessed them to remove the one part. They must have felt that they could get away with that, but you know, the breakdown voltage is going to be cut in half here. I think I tested this meter all the way up to 14 or 15 kV. But what ended up happening is the transient worked its way around this little plastic insert. And you can see I've bent another little plastic insert right here to increase the length of this and force the transient basically to have a further distance to go around. And that allowed me to continue testing this meter even higher than where it originally broke down at. You can see I've added a little bit of corona dope right in this area here. The only thing I'd like to show you is the switch contacts. As long as we have it apart, you can see that this one does not use any kind of dielectric grease on it. You can also see that there are no vias in the pads, and there's no places where the contacts will rub across a trace. So this switch design is pretty good. This is looking at the contacts. Again, a pretty decent setup. Another thing I'd like to mention is Hioki actually did reach out to me. It's probably been maybe 3 or 4 years ago. Whatever their offer was, I do remember that I declined them. Again, I don't normally accept any offers. There's no Patreon or any way to donate to this channel. Again, I just pay for this stuff out of pocket, except when it comes to Briman, and really that's because they're sending me a lot of meters that are pre-production, so we get an early look at them, and then I can actually help shake down the meter before they actually get released. I'm not being paid for any of that work that I'm doing with Briman. I do all that free of charge. You can see how these kind of fit together. And we have this plastic cover that goes over the top. And we have our detent spring, and you can see these are quite flexible. You may remember I looked at a Keysight meter, and that looked like they had used a glass-filled plastic for this detent spring. And of course we broke all the prongs on that during our 50,000 life cycle test. Oops. So you can see this little arrow here. We line these up to get it to the off state. And we put our little detent spring in like so. Make sure we don't have any garbage on our display. And it just fits back together like so. Notice this feature right here. And notice the insert on the cover right here. So this fits inside like so. And then you can see they have a metal insert for this screw. Mechanically, this is a really well-built meter. Again, this is pretty much what I would expect coming from this company. Let's just make sure I got this right before we button it all up. Yep. Just make sure the switch works right. And it does. Make sure it zeroes out. It does, no problem. Go ahead and tighten this up and put the rest of the screws in. Next, what I'd like to do is compare the backlight of these meters. So on the right we have the BM869s. This is the newest meter. In the middle we have the Hioki DT4282, and on the left I have my original Bryman BM869s. Now again, I had mentioned I had updated the firmware in this meter on the right. One of the big changes that they made was they increased the backlight timer. Let's just go ahead and we'll turn on all three meters. We'll go ahead and turn on the Hioki. You can see this backlight is going to shut off pretty quick. There was no way to extend the length of that, so that's a change that Briman made later. So if you buy a brand new BM869s, it'll have this extended backlight. Both are easy to read. I would say it's basically a wash between the two. Alright, let's have a look at the displays in direct sunlight. Here we have the Hioki on the left, my Fluke 189, the Brymen BM869s, and the new Bryman BM788 BT. I mean, even from back here, yeah, those Brymans, I like the larger display. This is my old Robbins tape eraser. You can see this puts out a AC magnetic field. So currently all these meters are attached in parallel. I'm going to be applying a 1 volt DC signal into the meters. Here we have the EEV blog 121GW. You can see it's reading spot on at 1 volt. Here we have the Unity UT181A. You can see it's reading 0.9993. And this is my Fluke 189. You can see it's 0.9997. This is my original Bryman BM869s. You can see it's also 0.9997. Here's the Hioki DT4282, and it's reading 0.9994. And this is the brand new Bryman BM788 BT. You can see it's 0.9995. And this is my Keysight U1282A. And you can see it's reading 0.9998. What we'll do now is expose each meter to this magnetic field, and let's see if it has any effect. And you can see no problem. No problem. Oh, right there. You can see it does affect the Unity meter. You can see with the Fluke, you can see it has a slight effect. A couple of digits, not as much as the Unity. Here's the Bryman BM869s. And it has no effect. It has no effect with our Hioki at all. Let's try the new Briman. And no effect. Let's see with our Keysight meter. And again, no effect. Let's just try this from the top. Yeah, looks like the one that's most affected is this Unity meter. Probably the worst meter I'd seen out of all the ones I've looked at was the Gossen Metrowatt, and that was the Ultra BT model. That had no shielding in it, so just holding your hand near the meter would cause it to read sporadically. Okay, I've changed all of our meters over to the millivolt range, and you can see I'm applying a 1 millivolt signal. Alright, again, just hit these with the tape eraser, and you can see now that is having some effect on our 121 GW. Same for our Unity meter. The fluke has some effect, but it's very little. Here's the BM869s. It doesn't appear to affect that at all. Here's the Hioki, and doesn't look like any effect. Meter has a shield in it, but yeah, no effect. Let's just try it with our key sight meter. See, that meter's off a little bit. Probably needs to be aligned. It looks like it has no effect on that meter as well. The two worst, it looks like, again, are this Unity UT181A and this 121 GW. Right there, I'm probably 4 or 5 inches away from the meter. Same thing with the 181. You can just see it's got a pretty big effect on both of these meters. But yeah, our Bryman BM869s, as well as the new Hioki, basically these are immune to this. Same thing with our brand new Bryman BM788 BT. So it looks good. Alright, we're going to try a little bit of high voltage testing. Again, the Hioki on the left and our two Briman meters on the right. Again, this is the one that's been modified. This is the original one that I purchased. Again, this one now being about 10 years old. Off to the left, we can see I have an applied kilovolt high voltage power supply. That's attached to all 3 of these meters sitting in parallel. We're just going to select the DC volts. So get these so we get a little bit of glare out of the screens. That looks pretty good. Alright, I'm going to start turning up our power supply. So here you can see, again, this meter is a 60,000 count meter. If we want to gain resolution, though, in the DC volt mode, we can select the 50,000 count mode, and we can gain that extra digit if we need it. Again, people talk about the instability of this mode. You can see that's not really an issue. All 3 meters are basically reading the same value. Let's try going up a little higher. It's 265 volts, 413, 660 volts, right there is where it overranges at 1,000 volts. Of course, the Brymans will read up a little higher. There's 10% higher right there. You can see no damage to the Hioki. Okay, again, all 3 meters are placed in parallel, and they're attached to our other high voltage power supply. Again, this power supply is going to be switching between 0 and some high voltage that's programmable. You can see it's currently running at 100 Hertz. You can see it's displaying roughly 1.47 or so volts AC. That's the same as our other 2 Briman meters, and the AC plus DC is 2.1 or so volts, and if we display that with the Hioki, you can see it's 2.098. So basically all 3 meters are currently tracking What I'm going to do now is start increasing the voltage. You can see here 112 volts, 112, 112. Let's go up a little higher. 562 across the board. All 3 meters basically tracking. And that is essentially the limit of our power supply right there. This will be switching between a negative and a positive rail. So here we have the DC voltage. Here we have our AC voltage. And here we have our AC plus DC. So you can see currently it's displaying 473 volts AC plus DC, and the DC voltage is essentially 0 or 18 volts. And again, we're at 100 hertz. Let's try changing that DC offset. So here we are with about 200 volts positive of DC offset. What I want to know is if that affects the AC plus DC reading, and you can see it does not. Let's try going up a little higher. So here we are with a 420 volts positive DC offset, and again you can see that's having no effect on the Hioki. Again, these 2 meters are basically matching. Let's try going negative with it. So here's a negative 213 volts DC, and again you can see the AC plus DC is tracking. Let's try going a little further. So here we are at a minus 479 volts DC, and then 472 volts AC. And again, you can see the AC plus DC is tracking between the 2 meters. So no problem with this whatsoever with the Hioki. Again, I want to be clear that a lot of the meters that I've looked at over the years have had a problem running this particular test. So that's not unusual. It's good to see that the Hioki doesn't have any issues with it. What I'm going to do is look at the small signal roll off for the 2 meters. You can see they're currently both displaying 1 volt, and this is at 100 hertz. What I'm going to do is just increase the frequency, and let's just see where the 3 dB point is. I'm going to change this to flip the 2 around, make it a little easier to read. So again, we're at 600 hertz right now. You can see both meters displaying a volt. See, the Briman is starting to peak up a little bit while the Hioki is starting to roll off. Here we are at 30 kilohertz. We're at 60 kilohertz. See, the Briman is no longer reading the frequency. Both meters are starting to roll off pretty good. Right about here. So there's the 3 dB point for the Briman at 490 kilohertz. See, the Hioki is peaking up again. This is currently at 2 megahertz. See, the Briman has had this nice gradual slope, but the Hioki continues to increase. Let's just go up by a megahertz. Here we are at 3 meg. Let's just see if we can find that sweet spot right about here. So this is 2.13 megahertz. Again, neither meter is very flat. Typically though, if I'm looking at AC waveforms, we're using the scope. I currently have a 200 hertz square wave applied, and that's a 20% duty cycle. We're just going to select both meters to the DC mode, and we'll enable Crest and peak. And you can see, at least for the peak reading, they're pretty close, so 1.42 versus 1.43. Let's look at the negative, or the minimum. So 1.435 versus 1.410. So again, fairly close. Let's try doubling the frequency to 400 hertz and see how they do. It's probably a way to reset these. I'll just cycle them through. Alright, so again, the negative 1.41 versus the negative 1.44, we'll call it. And let's see, positive 1.074 versus 1.419. This one is correct. You can see the Bryman's reading a little low. So at 400 hertz, there's already quite a bit of error. I wonder if the newer meter does any better. Let's just see here. Select in Crest mode. It's about the same, 1.072. So again, a little low with this meter. This is basically a MOSFET driver. I use this to test the continuity modes of the meter. This is currently hooked up to our function generator. Let me just give you an idea of the volume level of the 2 meters. You can see it reads roughly 10 ohms. Looks like this one has maybe a programmable threshold. Volume wise, the 2 meters are pretty close. You can see they're both reading roughly 10 ohms. Let's try speeding this up a little bit. This is at 4 hertz. Here we are at 10 hertz. I don't know if that flashing red would give you a seizure or not. That's pretty annoying. But pretty fast. Let's try going up a little higher. This is with a 20% duty cycle right here. This is at 30 hertz. And here it's nice and smooth with the Briman. You can see with the Hioki, it's missing beats every now and then. But probably for my use, both of these would be fast enough. For me, where this really comes into play is where I'm reverse engineering something. Maybe I'm taking a lead and I'm dragging that along an LCC device. So the faster that the meters respond, normally that's better. But it's interesting, I believe that you can program the threshold of this. So there's 20, 50, 100, 500 ohms. And again, that's not programmable with the Briman. That's a fixed resistance with this meter. Let's just see if that's really the case. Here's a 70 ohm. Here's 94 ohms, and you can see we're picking that up just fine. Let's go up another 10 ohms, and you can see it's no longer tripping. So let's increase this to 500 ohms. You can see it's reading that just fine. And let's increase our resistance. So there's 600 ohms. You can see it's no longer picking it up. Looks like that's the upper limit of it. So yeah, we're right on the cusp right there. It flips right at 500 ohms. So that's a nice feature on this meter, that you can program that threshold point, which I could never do with the Briman. This is a 3-phase converter. This is made by Magnatech. This is a CIMR V7 AM2 1P5. I've had a problem where some of the meters I've looked at have problems reading voltages off of these variable frequency drives. What we're going to do is just select both of these meters to their AC modes. And let's turn this drive on. And we'll go ahead and enable it. You can see there's quite a bit of a difference between the two, about 259 versus 244. You can see the Hioki's reading somewhere up around 60 kilohertz. The Briman is displaying about 1.8 kilohertz or so. What I'm going to do is just select the VFD mode on the Briman. Try to filter that down, and you can see now it's reading 60 hertz and about 230 volts. This is probably correct. Now with the Hioki, they have a filter feature. Let's go ahead and enable that. And you can see it's now displaying 60 Hertz at 229.3 volts. So the two meters now basically matching. You can see we're back in the motorcycle trailer. Here's my old GS. And here's my Hayabusa. The Hayabusa is actually a street legal bike. This has all been airbrushed by a buddy of mine. You can see the detail of it. You can see the Hayabusa is turbocharged as well. Up in here, and there's the wastegate. A lot of skulls on this bike. My wife wasn't too keen on the paint job. Looks like the death machine. Next we're going to be running a chemical test on our little Hioki meter. So first we've got some VP C16 fuel. This is what's used in the GS bike. Let's just see if this strips our Yeah, let's see what it does to the display. And no damage there, but that's definitely lightened up that A a little bit. Not as bad as some of them that I've seen, but it looks like that's actually eating the plastic here a little bit as well. So this is a little bit of methanol or wood grained alcohol. Let's just try the same letter, I guess. Oh, it's a little bit much. And that does not seem to be affecting it. Let's just try the display. Those Anec meters, man, this stuff just ate the plastic. Turn the display into frost. You can see that's had no effect there. Let's just see about the lettering. Yeah, no problem, but that gasoline has definitely affected the plastic here a little bit, as well as the lettering. Not as bad as some of them. I've seen that strip the lettering right off of some of the cheaper meters. You'd think with some of the meters that's just basically immune to these chemicals. I'm surprised that they all just don't follow the same recipe. If I get the meter out here in the sunlight, get a better look at this. That gasoline has definitely had an effect on the plastic. Here we have our 2-inch slab of oak. Again, we'll be performing a drop test approximately 1 meter up. Let's try it on the face. See, it turns on just fine. I'll go ahead and functional test it, but it doesn't look like any worse for the wear. We're going to move on to our potentially destructive test. We're going to start with this piezo grill starter. Again, the Bryman BM869s survived this testing just fine. Basically what we do is we apply 5 transients, both positive and negative, and we do that by converting the 2 leads. And we do this directly to the inputs of the meter, with the meter set to all the modes except for the current inputs, and then we'll functional test it after we're done. That's assuming that the meter doesn't die midstream, and you can usually tell that because the screen is going to go blank or something. So here we go. Alright, let's just check the resistance real quick. Normally what you would see with the meters failing is it'll take out that high-speed clamp, and this would basically be reading some low resistance. The fact that it's reading high, it's a good indicator that the meter is not damaged. just do a real quick check again. This will be a dead short, 100, 1K, 10K, 100K, 1 meg, 10 meg, and let's just try it with capacitance real quick. So again, this will be 150 puff. Again, I have not zeroed this out. Here's a 0.1. Here's a 1 nanofarad. That looks all fine. Let's just check it in the DC volt mode real quick. Again, this should be 5 volts. Looks good. I'll go ahead and run an extensive functional test on it, but it looks like it survived that testing just fine. Alright, so our Hioki survived their gas grill test. Next we're going to be using our homemade ESD gun. Again, the pulse that this puts out is very close to the IEC standard, where if you look at the current profile off of this gas grill igniter, it's actually quite a weak pulse. So again, we'll be applying 5 transients, both positive and negative, with the meter set to each mode. So here we go. And again, we'll invert the leads to get our negative transient. That's it. Again, let's just check the resistance mode real quick. If it reads an open, I'd say we're in pretty good shape. Looks like it does. Alright, I'll go ahead and functional test the meter. Alright, our Hioki survived that testing just fine. I want to show you real quick here. Again, so if we just place this thing into conductance mode, again, this is with our 1 gig ohm resistor. This should read 1.0. I'm holding on to the leads versus normally I've got them clipped onto these and I'm not anywhere near this box, but the leakage current of the meter hasn't changed at all. So I'm saying that these ESD tests have not degraded the performance of the meter at all. Alright, next we're going to be using this transient generator to supply a full wave rectified 220 volt AC signal to the meter, and then we're going to select all the functions of the meter and see if that causes any damage to it. Let's go ahead and select AC volt mode, and we'll turn on the output, and you can see our meter is displaying 117 volts or so. Let's try it in DC mode, and you can see it's 230 volts peak. That's correct. Let's just go ahead and cycle through them. And that's it. I'll go ahead and functional test the meter. Next we're going to be applying transients to the meter using our transient generator here. Again, this is a custom made generator. We're going to apply 5 transients, both positive and negative, with the meter set to each mode, and then we're going to functional test it. Again, this is a exponentially decaying waveform, and I want to be clear, I've had various people suggest that I was essentially just hooking these up to a capacitor bank. Again, that's not at all the case. The open circuit voltage waveform off of this is actually modeled after the IEC standards that these meters are normally tested to, except for the fact that I've doubled the full width half height. Of course, those IEC standards call for a combo generator. It's called a combo because they're interested in 2 different waveforms. So you have the open circuit voltage as well as the short circuit current. Now, the short circuit current of this does not even come close to matching the IEC standard. But again, I'm not really interested in safety on this channel. What I am interested in is how electrically robust these meters are. So this transient generator is limited to about 20 joules. But again, if the meter does not break down, all that energy is dissipated inside of the transient generator in the output network. So typically that energy is not being dissipated by the meter itself, only if something goes wrong. Now, I'm not going to be using the oscilloscope today to monitor these waveforms. We're still in the summer months, so the room up here is a little hot, so I don't want the added heat. But if it does fail, we'll probably hear it. Typically the meters will click, you can hear them break down, or you'll see the display start to flake out a little bit. Anyway, so here we go. This will be our first 5 transients. Again, this will be a 1000 volt peak with 100 microsecond full width half height and a 2 ohm source impedance. Then we have to invert the leads to get the negative transient. Okay, that's it. I'll go ahead and functional test the meter. So our Hioki survived the 1000 volt peak. I've reprogrammed our generator for a 1.5 kilovolt peak. Again, that's a 100 microsecond full width half height with a 2 ohm source impedance. Alright, that's it. I'll functional test the meter. Okay, our meter passed functional just fine. I've reprogrammed our generator for a 2000 volt peak, 100 microsecond full width half height with a 2 ohm source. And that's it. Alright, the meter is fine. I've gone ahead and reprogrammed our generator for a 2,500 volt peak. Again, this will be a 100 microsecond full width half height and a 2 ohm source impedance. And that's it. Alright, the Hioki passed that test just fine. I've reprogrammed our generator for a 3000 volt peak, 100 microsecond full width half height, and again a 2 ohm source impedance. And that's it. Well, it looks like we've damaged the meter. You can see I've got currently attached a 100 ohm resistor. It's reading 67 or so ohms. This is with a open circuit. You can see it's reading basically 568K. If we go to temperature, again, this should be roughly 500 degrees Celsius. You can see it's reading 55. If we go to conductance, with the leads open, you can see it's reading 107, 108 nanosiemens. Let's try it in capacitance. And this is our 150 picofarad. And you can see it cannot resolve that. Again, this will be roughly 2.5 volts. And it's at 60 hertz. This is going to be 3.5 volts AC plus DC. This is at 30 hertz. You can see that's all fine. If we go to the DC volt mode, this should be 5 volts. That's fine. And here we are in the AC volt mode. And this should read 2.5. And you can see that's fine. So probably something on the source side got taken out. Unfortunately, that's the side with the PTC. Remember, I had shown where they had removed that one surge rated resistor. Again, I'm quite surprised this did so poorly because the lower cost meter that we looked at previously did so well. Let's go ahead and we'll tear this thing apart and let's see if we can figure out what went wrong with it. Alright, so if we look at our meter here, this is our high voltage input. It goes through this PTC. This is the side that we're interested in. Goes through this surge rated resistor. Again, that goes to the gas discharge tube and then back to the common point. This point here, we're expecting there to be a high-speed clamp. This goes up to this small SOT23 right here. Yeah, so that's going to the return point. So from here to here, these two are connected, and then from the top to this side here, these are connected, and again this is going back to our surge rated resistor. If I had to take a guess, it's probably one of these three components. If we check these across, are these a short? See, that's reading like 9 ohms. This one's reading like 11. What are we getting here? That's like 2 meg. And from here to here, like 4 meg. Let's just try this in transistor mode. Yeah, these are basically looking like a dead short. Let's just check this one real quick. 0.7 and 0.7 as well. Yeah, let me see if we can identify those parts. Alright, so looking these up, these two appear to be Zener diodes. They're rated at basically about 3.9 volts. This is potentially a silicon diode. Because I'm seeing 0.6 volts or so across this part here, I suspect it's these two Zeners that have failed, because these two are in series and it doesn't look like the center node goes anyplace else. I think what I'd like to do is just lift one of those off of there real quick, and let's just see if that clears this fault. Doesn't really matter which one we remove. We'll just go with the bottom one here. And let's just check this out of circuit real fast. Alright, let's see what we get. So, this direction here, using diode check, it's 0.0035. And this way here, 0.0035. Let's just have a look at this other one. Is that the same? Yep, 0046 and 0043. Again, 0.690, and going from here to here, 0.69. My guess is it's these two Zeners here are essentially shorted. I'm just going to go ahead and pull the second one off real quick. As long as I got the soldering iron heated up. And we'll check this one out of circuit as well. Alright, what do we got here? 0.0043. So yeah, these two are probably bad. Let's just snap our switch in real quick. And let's just see if we can fire this up inside of the case. And we'll select the resistance mode. Yep. Oh, had it there for a sec. And there you have it, so 600 meg. So that's cleared our fault, but unfortunately I don't have any part like that here on hand, so I'll have to order those up and then we can go ahead and replace them. So did I make a good decision 10 years ago when I brought the Bryman BM869s? You know, this Hioki does have some nice features that this Briman doesn't have. But one of the reasons that I wanted a handheld meter is to get something that was a little more robust than the bench meter. So the Briman is definitely far more robust than what this Hioki is. Again, I don't know why that is, because that other Hioki did so well. It's quite surprising to see this thing fail. The other thing too about this Briman, I do like the fact that it has this two thermocouple inputs. That again is a feature that I've liked having. I like the fact that it's got this 500,000 count mode. Another feature that I like with these meters is the fact that they remember the last settings that you used. So I know a lot of people don't like that, but I find that that feature saves me quite a bit of time, so I like having that. So if I had to choose between these two meters today, which one would I buy? I would still buy this Bryman BM869s. For my use case, this is definitely a better meter. Well, I think that's going to be it. We'll see you in the next video. Later.